So in the last class, we started to talk about the SVM, support vector machine. So the idea behind the SVM is we try to find what at least the original motivation is we try to find linear separator, okay, linear separator, which is basically just a linear line, which can separate like two group of the objects. Now, in the ideal way, as we talk about it, if there are two groups in here, you have a blue group and a red group, and they can be perfectly separable, right? They're perfectly separable in this two-dimensional space. Now, there are many ways you can draw the line to separate these two groups. Then the question is, what is the best way? Right? What is the best linear line that can separate these two groups? You can do it this way. You can do it this way. Then how do you define what is the best linear separator? Now, the idea is the intuition will be if we draw this is a two, so like the convex hull for each group. Okay. Now this is when you draw the outer points of each group. Okay. This is the group so like the shape they form has to be a convex hull. Okay. Convex hull. It has to be convex. Then if you can find like 2 points, okay, that are closest, okay, they're closer to each other from this two convex hull, then you draw a line in between, like from C to D. Then in the middle point, you draw another line, which is kind of like a perpendicular to this CD, the vector. Then that line should be the best separator. So the best separator is somewhere like in between. This is a two groups, right? Two subgroups, and then it doesn't too close. It's not too close to the upper one, or not too close to the lower group. It's somewhere in the middle. So then that's really best. Then that's the intuition. So mathematically, how we can define this problem? Okay. This actually can be defined as so-called classification margin. The distance, okay, the distance from any point to the separator is basically R. The distance is R, which is given by beta transpose X plus B divided by the norm of the beta. Okay. Now, in here, essentially, if we have a separator, okay, if a separator like in the middle line. Middle, this is a solid line. You see, there's a green line here. This middle line, if it's defined by a linear the system, which is called beta transpose X plus B, then any point, okay, see this red point, the distance to this line is called R. This R can be defined. Any distance to the line can be defined given by this. Now, how do you know this distance is given by this? That's what I wrote in on a black whiteboard. Basically, what is giving you the sort of like the simple derivation, right? So if we let L be the hyperplane defined by our separator, which is beta transpose X plus B equal to 0, right? So this is a hyperplane in the high dimensional space. Now, this is a simple property, right? So for any 2 points, x1, x2 in L, right? That basically means you have beta transpose x1 plus b equal to 0, beta transpose x2 plus b equal to 0, right? Because they are on the hyperplane. So therefore, if you subtract these two, then you have beta transpose x1 minus x2 equal to 0, right? Because the beta transpose x1 equal to minus b, beta transpose x2 equal to minus b, so they take the difference is 0. So this is the first point is clear. Second point is for any point x0 in L, then beta transpose x0 equal to minus b. That's just basically you plugging x0 into here, you're getting beta transpose x0 equal to minus b. So that's also clear. Now let's define the beta star equal to beta divided by the normal beta. So a vector, okay, so if say beta is equal to beta 1 up to like beta p, okay? Norm basically is defined, you can define it as Euclidean distance, okay? It's the square root of beta 1 squared plus beta 2 squared and plus beta p squared. Okay, this is a norm. Basically, just normalize the distance, Euclidean distance. So if we define the beta star to be beta divided by the normal beta, so therefore the norm of beta star is going to be equal to 1, right? So then the beta star actually is a vector norm to the surface of the L. So why the beta star is a vector norm to the surface of L? Because if you have this is a this is a line defined by you have 2 points x1, x2. These are the 2 points on the line. You have beta transpose x minus beta x1 minus x2 equal to 0. X1 minus x2 that this is the point from the x1 to the x2, right? Now then this vector, okay, beta transpose x minus 2, that means beta is going to be perpendicular to the hyperplane, right? So therefore the beta star is a vector norm to the surface of the L. So this will be the direction beta is perpendicular to the surface. Now for any, okay, say this is beta. So if you have any point x, okay, we have any point x. Now the distance between the x to this hyperplane. What is distance? So let's say we're choosing another point x0 to there. The distance of the x to the surface will be this part, right? Gonna be distance is gonna be perpendicular to the surface. So this is the distance. Now this distance you can also build as okay. So this is so for any vector x0, you can have a vector from x0 to x. This is the distance. Now the distance of x to the hyperplane, you can also build as a projection of this vector projected to the beta, right? The beta. So this is you can also view the distance of x to the hyperplane would be the vector for choose any point x0 and then make the vector between x0 and x. This vector is projection to the beta would be the distance for the x to the hyperplane, right? So and this distance is defined by the beta star transpose x minus x0, right? It's defined by this vector because this is a projection. So then because we know beta, this is the beta star is equal to beta. So this guy is equal to beta over norm of the beta times x minus x0. Okay, beta transpose. So therefore, you can have here, you have beta norm, you have beta transpose x, then you have beta transpose, you have minus beta transpose x0. And we know beta transpose x0 equal to minus v, so therefore this is a plus v back to the original equation. So therefore the and which is beta transpose x essentially is equal to fx, and down below the norm of x, this is can be viewed as a norm of the first order derivative of fx, right? It's essentially the same because this is a fx derivative with respect to beta is with respect to x equal to beta, right? And this is just another way to look at it. So what I wrote on the whiteboard essentially is just to is the explanation for the first line. Okay. So therefore, to any point x in the space is distance to this is a separator beta transpose x plus b. You can define as beta transpose x plus b divided by normal beta, right? So this is a so we have this point being so this point we saw like we have slap this equation. All right, is this clear? Any question on this? Okay. Now the data points closest to the hyperplane we call the support vectors. So see you have in the separator, which is defined in the middle here, this is beta x plus b equal to 0. Now, those points, which are the points are the closest to this hyperplane, okay? This hyperplane we call the support vectors. We're gonna come back to why we to the point why we call it support vectors. But now just to see this points will be this points will be the points gonna define the separator, okay? Define the hyperplane in the middle. So the margin, okay, the margin rho of the separator is the width of the separation between the classes. This is called margin. Okay, this is called margin. Say you having this vector. This is a but this is the point is the point. But this point can be defined x1, x2, up to xp, right? So this point lives in the p-dimensional space. So therefore, the point itself is also a vector. Okay, so that's why it's called a supporting vector. Now, the distance between, so you're having the closest point to the from the red group to the separator. You also have the closest point from the blue group to the separator, right? So therefore, the distance between this is the closest the points from both group, okay, is defined by the distance is given by this is we call it a rho, which is defined as a so-called margin. So the margin of separator is the width of separation between two classes. So our goal then the separator essentially is living in the middle of the separation, all right, to the separator, to the margin. Now our goal is try to maximize the margin between these two groups. Okay, so this is also called the maximum margin classification. So therefore, we're maximizing the margin is good according to our intuition theory, right? So if you look at it, it implies that only support vectors are important. Other training examples are basically ignorable. So if you want to define like the largest, okay, larger distance between two classes or two groups, then this distance can be defined by this so-called margins, right? This is margins. Now, is this margin? Is this concept margin? Is this clear? Is that quite clear on this? Is I mean, if you have never heard of it before, is this margin could be a little bit confusing. That's basically is you have two groups, right? You have two groups. Then you can draw the two convex hull for each group, and the margin essentially is the distance between any points. Okay, the smallest distance between this is the any point leaving this is the convex hull. So you pick any points from the left group and pick a point from the right group. Find the smallest distance between these two. That would be this margin. Because then you cannot find. This is basically is if you are familiar with in the unsupervised classification. This is like when you try to find the distance between two groups. You can define distance between like centroid of the two groups, right? You can define by the like a pairwise distance, or you can define by the minimal distance. The minimal distance defined basically is by this is like any the points. You can find what is the minimal distance, okay, between the two groups. So we basically try to, if we can find this is a so-called margin between the two groups, and then the separator, the best separator is kind of like is going to be live in the middle of the separator, right? The separation region. So the goal is we try to find this is a line which you can maximize our margin. So some statistical learning theory, this is a miscalculation error under the function complexity bound generalization errors. And this is functional complexity. This is just like general. So the more complex of your separation function, okay, the more complex your model is, usually the higher probability of overfitting. Okay, so because the more you're having like a very complicated, this is the model to separate the two groups, then the so-called generalization error should be logged, because then that means your model may be trained to so tailor to your training data. Therefore, when you generalize to the test data, then you may have overfitting issues. So this is sort of like a general theory. We don't want our model to be complex. Okay, so at the same time, we also want to achieve the similar accuracy. This is I didn't spend much time to talk about the model selection. So model selection essentially is a balance between, or the building model. Okay, building a model essentially is a balance between the model accuracy and the model complexity. Okay, so which means you want to build a model which is as simple as possible, but at the same time it also can have sufficient accuracy. Okay, because model complexity and model accuracy, these are like two conflicting the property. Because the more complex your model is, then the easier or the smaller error for your training data. Okay, if for example, I can give you a simple example for the for this point. Say for example, if you have like 2 points, right? You have 2 group of points here. You have this is a you have this is a circle and the cross, right? Now, if you want to draw a line, if you want to draw a linear line, try to separate these 2 groups. This essentially is impossible, right? Because no matter what line you draw between this cross and the circle, you're not gonna draw a linear line to fit it. This is what polynomial? Yeah. So, but if you so that means the simple model is for the linear model, simple model, you will not be able to separate them. But if you can, well, if I draw another line here, it's polynomial is not even going to separate it. Okay, but if you are making a really complicated model, you can draw a line like this. Okay, you can draw a line basically. Well, I can do this. And then somehow cover it back. Okay, in some high dimension space, I can make it. This is just essentially like a circle, right? If you can make it somehow a circle, if I can make a really complicated the model, which is can making the boundary like this, I can perfectly separate this as a 2 group. Okay, but then this group may not be able to generalize to the task data. So this is this model will be much more complex than the simple linear model. But then with more complexity, but then its training error is going to be small. However, the test error may not be small. So that's what I mean. Usually, when you try to build a model, it would be a balance between your model accuracy, which basically training error, and the model complexity. Okay, so this is a point I'll try to make here. Maximizing margin essentially is minimize the complexity. Okay, we're gonna see. I'll show you in the next slides. So then what we try to do is we try to eliminate the overfitting, which is eliminate. I put a quote because the overfitting you can never really eliminate them. We try to reduce it, okay, as much as possible. So the solution depends on only on the support vector, not the number of attributes. So this is also the point we're gonna see in the next slides. Now, why the margin? So the relation between margin and complexity is the smaller the margin. Okay, when you try to define this, the smaller the margin, then the more complex the model. Because when you have in a smaller, you have a skinny margin. This is more basically model is more flexible. So you can you have this smaller margin, then that means you can have multiple ways to place it, right? So therefore, then the more flexible the model is, then therefore the more complexity in the model. Now, if you have this is a fat margin, then essentially that is less flexible. Okay, it's less flexible. So you only have one way to do it. So therefore, you have the fat margin. Essentially, is have a simpler model. So therefore, this is the point I'm going to make here. Then the maximizing margin basically minimize the complexity. Okay, so this is which is good. So therefore, what we try to do is we try to maximize our margins. Okay, that maximum margins. Now the question is how, okay? So this is all right now is all based on the intuition, and it's all based on this is our like more like the description of the property is the things we want to have. So in the next few slides, what we try to do is we try to formulate, okay, our intuition into equations, and then using that equation, then you derive the to make it into like a sort of optimization problem and solve it. Okay? So if we can assume all the data is right now, what I'm trying to do is I'm assuming all the data for the two groups, they are perfectly separable, okay, by eyes. We're gonna generalize later on to say when the data are not perfectly separable, how we can handle it, okay. So for now, let's just for the cases is all like in this is a perfect world. We have two groups, and these two groups can be perfectly separable. What we try to do is try to find the best separation line for this is a so like optimal condition. Okay. Now, assume all data points is at a distance larger than 1 from the hyperplane. Then what basically we can formulating the two then we can the following two constraints we can define for a training set xi yi, which is if you have in the yi, if you beta transpose xi plus b, if it's bigger than or equal to 1, then if yi equal to 1. If this is a beta transpose xi plus b is less than -1, if yi equal to -1. That's basically saying if the distance is more than 1, okay, I'm going to say it's in the yi equal to 1 in one group. If the distance is less than -1, they are signed distance, right? Because this is a signed distance. So it's less than -1. I'm gonna make it this is a y equal to -1. Now here is the question. Now I assume I assume I have this two group, right? I have two group. I draw a line in the between. So this is beta transpose x plus b equal to 0. I assume the closest point to this is a distance is going to be 1. Okay, can I do that? Is it true? Like it's for any points in the from the hyperplane, the distance, the minimum has to be 1. It could be possible this distance be less than 1. Like if I have beta transpose plus b, this is my separation separator. Then I have another point in here. Can I say any points? The distance between any points to this separation is going to be at least 1. Can I make that statement? At least, yeah, at least 1. Could be, can it be less than 1? Could be like the distance could it be like 0.5 or 0.1? Huh? Yeah, but it can be, but then you're making the problem is gonna be more difficult. But now I'm just saying if I can fix the lower bound, all right, fix my bound at a 1 or -1, you're gonna make my Fourier derivation much easier. So, but it is but I'm right here. I'm assuming all data is at distance larger than 1 from hyperplane. Is that a problem in here? It's actually not, okay, because say you have x, right? So the maximum distance is beta x. The beta transpose x plus is actually the distance is gonna be this, right? Now suppose this is your distance is actually some arbitrary distance, say lambda, okay? All you can do is basically you can just divide your beta and the b by the lambda. Okay, so you just divide, you renormalize your beta and b because beta and b are parameter. Okay, so you haven't really defined what the value of beta and b is. So that's the point. That's a parameter we have to maximize. So if your distance is not 1, essentially you just rescale your beta and b. Okay, so basically by define the distance between this beta transpose xi plus b bigger than or equal to 0 or bigger than or equal to 1 or less than or equal to -1. What we try to do here is we can see that because if the beta and b are not satisfied, then we can scale it up or scale it down. Okay, so that's this is perfect fine by making this assumption. I assume all data is larger than 1. Now now we assume all data points is going to be bigger than or equal to 1, and for this point is sitting on the closest point, right? The distance between the closest point to the separator is going to be 1. Okay, this is going to be 1. This is going to be 1. Okay, well, it's actually -1, but since the distance, we can just say this is equal to 1. Now, for support vectors, the inequality just become equality, right? That's if you're sitting on the boundary of the two groups, then that's distance exactly 1. So then, since each example distance from hyperplane is, as we said before, is r equal to beta transpose x plus b, this is divided by the norm of the beta. So therefore, the margin rho essentially is 2 divided by norm of the beta, right? Because the distance from here to this one is 1. This is 1, right? So therefore, the distance, because this means if you have a line here, this line is going to be beta transpose x plus b equal to -1, and this line basically beta transpose plus b equal to 1, right? That's this will be the two boundary lines, right? Two boundary lines defined by that, because we assume the points at the boundary is distance to the separator is exactly 1, right? Exactly 1. So therefore, then the margin rho is just 2 divided by normal beta from this equation what we have derived before. Okay, this is this clear, or this is any question on this? Okay, it's good. So now you can see we established the margin rho, the relation between margin and rho under the relation between rho and beta. Okay, beta is our coefficient, is one is a parameter we try to, because beta defines our separation hyperplane, right? So now the beta is related. Now we relate the beta with the rho. Okay, so the goal. What is the goal? So what is our problem here? What do we try to do? So we define the margin, and what do we try to do here? We try to maximize it, right? So therefore, our goal essentially is try to maximize our margin. Okay. So the problem now is become maximize our margin rho, which is essentially is equivalent to maximize is 2 divided by norm of beta. Right? So with respect to beta. Now, is this maximization is a constrained maximization or is unconstrained? Do we have any constraint to this maximization? We have some constraint, right? Because the constraint would simply be we assume every point is at least 1 from the separation, right? So therefore, the constraint is going to be if yi equal to 1, we're going to say beta transpose xi plus b is bigger than or equal to 1. If yi equal to -1, beta transpose xi plus b is going to less than or equal to -1. Right? So this is our constraint. So therefore, you can see now we basically has transformed our intuition, which we try to maximize. You have two groups. We are maximize the margin, right? Try to find the best separation line. Now you transform to mathematical equation formulation, right? Formula we can work with. So this will be our problem. Okay. So we try to maximize our margin, and then we subject to this constraint, okay? Subject to this constraint. So now essentially, this is exactly what I'm going to show you guys in the next slides. So we try to, so the linear SVM is, we can formulate this is a quadratic optimization problem. We want to find the beta and b such that the rho, which is margin, is maximized, and for all this is for this points xi, yi, you have subject to these two constraints, right? That's this is the this is a one problem. Now what is down below here? This is a better formulation. Now maximize the margin, essentially because this is the beta is in the normal beta is in the denominator, right? So essentially is we can say maximize margin is equivalent to say minimize this is a quadratic form, right? It is minimize half of beta transpose beta, because remember what is a normal beta is a square. The normal beta is equal to square root of beta transpose beta. You can write it like this, right? Essentially is equal to this guy. So therefore your minimize your maximize, this is a 2 over the norm, essentially is the same thing to minimize this is a beta transpose beta, right? I have this half in front of it just for the mathematical convenience, okay, you're going to see in a second. So then this is the maximization problem is equal to this minimization problem down there. Now for the inequality constraint, we can write it in a like a more concise way. That concise way is that we can see for all the xi, yi, we can see yi times beta transpose xi plus b bigger than or equal to 1. Okay, this is we can do that, right? Because if you yi equal to 1, this is equal to yi equal to -1. Then you multiply by yi -1 on both sides. This is you will become also bigger than or equal to 1, right? So therefore, this is then we can write this as two sets of inequality basically into this is the same equation. So yi times the beta transpose xi plus b bigger than or equal to 1 for both. So therefore, this problem right here, this is our so like the formula we're gonna work with. Now, how do we minimize how do you minimize this problem? Say that again. Double differentiation. Yeah. So the problem, once you have this problem here, this is essentially transformed to our like the formula you are familiar with, right? Like this essentially is a constraint the minimization problem, right? We can use Lagrangian the method. That's just define Lagrangian function. Then this is you can work with the Lagrangian. This should be fine. So what is a Lagrangian? So the Lagrangian function essentially is what? Is equal should be half beta transpose beta. Okay. Then I said is plus lambda times the inequality, right? So if this is inequality, and the lambda has to be bigger than 1. So how many inequality I have here? Suppose I have n data points. How many inequality I have here? N of them, right? So for each data point, you have one inequality. Now, because this is a bigger sign. Because remember when we define our minimization problem, our inequality is less equal to, right? So because this is bigger than equal to, so therefore I can use minus. Okay, I can use minus sign. So this is going to be minus the. I just want to make sure I'm using this. Okay, using the summation I from 1 to n. That's using alpha I to denote the Lagrangian multiplier for each equality. Okay, so this is going to be equal to alpha I times, then I have here is yi times beta transpose xi plus b minus 1. This guy. Okay. So your Lagrangian, the function is should be the one in the should be given by this guy, right? Equal to, so your object target function half beta times beta minus, then you since having n inequalities, so you using your Lagrangian multiplier alpha I times this inequality, because this inequality is bigger than equal to, so therefore when you having the form here is negative sign instead of is a subtraction instead of summation, right? Now this is subject to the constraint is going to be alpha I is bigger than equal to 0, right? Alpha I is because your Lagrangian multiplier has to be positive. Now, how do you solve this problem? You can just do like use gradient method, right? Which is fine. So you can just take the gradient of beta and then try to solve it numerically, which is fine. But then the issue is here, the points in the your constraint is actually pretty there's a lot of constraint there. Okay, so the solution is not that easy to see what the thing looks like. Now, then this is where the Lagrangian dual properties problems come into handy. Particularly if we can look at the Lagrangian dual problem. Later on, when we extend it to when we allow the two groups, they are mixing together. In other words, if they're not perfectly separable, we introduce the concept of slack list, and also introduce the concept of the nonlinear SVM. Then the dual problem is actually make much more sense. You can see that. So let's see what is the dual problem. Okay. So let's use LP. You know, this is our primer problem for the Lagrangian function, right? This is our prime problem. Now our dual problem to essentially we want to minimize this with respect to beta and b. Okay. Now the dual problem we want to maximize of this guy. The dual problem is going to maximize this. What is LD here? Is basically LD is equal to want to minimize. This is a beta and b respect to the Lagrangian function, right? Remember the Lagrangian dual problem. The primary problem I can formulate as a min-max problem, right? Min-max problem, and then this is actually equivalent to the Max-Mealy problem. Okay, Max-Mealy inside here you first in Max-Mealy say you want to minimize the beta and the b first, and then you get a function of alpha I. Then in the dual function, you try to maximize this LD with respect to alpha I, right? Remember, if you forgot, then you can go back to review that lecture. So for the dual problem for the LD, okay, let's see what is LD. LD, we want to minimize this LP first. We want to minimize this Lagrangian function within the alpha I being given, right? So we fix. So we first fix alpha I. Let's see what is form of this for the beta. So DLD beta, what is it? DLD beta. So this is for the first one. This is just equal to beta, right? So this is this is a quadratic form of beta, and the derivative is just beta. Now minus summation I from 1 to n, you having the second term, so you're having alpha I, yi, beta I. So for all the rest, the b part and the minus 1 part is just constant with respect to beta, so they can be gone. Okay, so we don't need that. So what we have is this is the derivative with respect to alpha I, yi, beta transpose xi. So beta transpose xi can also be, this is because they're vector, is equal to xi transpose beta. Okay. So therefore, the derivative of this second term is just basically alpha I, yi times of xi. Okay. So then this will be the second term. Therefore, this is equal to 0. So given to say beta is going to be equal to summation I from 1 to n alpha I yi of xi. Notice here alpha I is a Lagrange multiplier, is a scalar. Okay, yi is the classification is equal to 1 or -1 is also a scalar. Xi is a vector, right? It's a vector length of features. Xi is a vector. So therefore, this beta is a summation of this is a bunch of vectors. Okay, it's sort of like you can think about a weighted vector. Okay, we are apply to that. So it's a summation of this xi's or the different points. dl db, this is equal to what? So if we respect to the b, then this does not have b is gone. Then inside here, -1 doesn't have b is gone. So then the first term does not have b can also be gone. So then this is a b. Basically, this is you only have alpha I and yib, right? Alpha I yib. So that's a contains b. So this is going to be equal to negative summation I from 1 to n alpha I yi equal to 0, right? Because you're taking derivative with b, so it's going to be equal to this guy. So the second thing, this is basically saying, summation I from 1 to n of alpha I yi equal to 0. Okay, you have this two equality being given. Now let's plug in this beta back to the Lagrange. Okay, we want to get an LD, right? We want to have an LD. So therefore, then what is LD here? So if we plug in this is 1, 2. Okay, if we plug in 1 and 2 back to our original Lagrange function, so therefore LD is going to be equal to half of this is summation of alpha I yi xi transpose, right? So this is our beta transpose times summation alpha I yi xi. Okay, so the first term, this is your half of beta transpose beta. Okay, this is given by here. Then you minus the first term is alpha I yi xi transpose beta. Okay, let's just using that term. So minus summation alpha I yi. Okay, your time here is xi transpose beta transpose times beta. Okay, beta is equal to essentially beta is this side, so summation alpha I yi xi. Okay, so alpha I yi xi transpose beta, so that we keep that. And the beta will just replace the summation alpha I yi xi, right? This is going to be the first term. The second term is going to be summation alpha I yi b, right? Summation 1 alpha I yi b. So minus summation alpha I yi times b. Since b doesn't have I, so I can just put in the b up in front. B times summation alpha I yi, right? So this is going to be the second term. The last term is going to be summation alpha I to the -1, right? So therefore you have negative is positive. So therefore you have summation alpha I. Okay. They are all summation is from 1 to n, right? It's from 1 to n. Okay. Now, if you look at this LD term, okay, it looks pretty complicated. But if you look at this term, from equation 2, we have alpha I yi summation is equal to 0, right? So therefore, this term is actually gone. Right? Because it's based on the second equation, so this term is gone. If you look at this, the first term, this guy and this guy, they are essentially the same. If you don't look at coefficient, essentially the same. Is summation y, because alpha I yi they are scalars, okay? So they are transpose just itself. So therefore, this thing right here, these two terms, they're actually the same. Okay. So therefore, you basically this LD, so summation of alpha I will keep it the same. Okay. Yeah, minus half. So essentially, it's going to become minus half. Okay, this will become minus half. You got a summation of summation. This suppose is I and j. Then this is going to be alpha I yi alpha j yj of xi transpose xj. Okay, So then the dual function is essentially you can simplify into this, right? Simplify into this. Now this, let's write this alpha j of this is yj, right? So you can see the function essentially is become this, because remember we want to maximize this alpha I with respect to this thing, right? To this thing. And of course it's going to have a subject, right? You want a subject to alpha I is bigger than or equal to 0, right? So essentially this is our dual problem, okay? Dual problem. We can then we can work with it. This actually is pretty in terms of this is the first the target function LD. Essentially, if you look at it, right? Look at it. Essentially, it's just a quadratic term, right? Essentially, it's just a quadratic term for the alpha I and subject to a linear constraint. So this problem is a very standard. The optimization problem. Okay, so if you plug in any like a quadratic the optimization function, then they should be able to solve it. Okay, it's very simple. Now let's look at it. What is this solution look like? Okay, this solution again, we are not going to be able to find a closed solution from it, but we can check some property of it. Okay. For this prime function, remember we have a KKT condition. What is a KKT condition? The KKT condition basically say by KKT condition, right? By KKT condition, what we essentially we say is alpha I times yi beta transpose xi plus b minus 1. This you have to equal to 0 for all I, right? Because this is you have an inequality constraint. Then from the KKT condition, you say the Lagrange multiplier times the constraint, the inequality itself, it has to be equal to 0, right? This is what we so this is the point. This is the places where like I did an introduction to optimization in that lecture, although it's very simple. Okay, but I feel if I don't do that lecture, if I directly jump to this place, you probably will be too much for you to memorize. But once I did that introduction, and now by the if I say KKT condition, you guys should be be familiar with this term. Even you don't even forgot, okay, you can go back to check the notes. So if you have this condition to be satisfied, that means if yi times this beta transpose xi plus b minus 1, if this is not equal to 0, okay, then alpha I has to be equal to 0. Okay. This is not this is greater than equal to 0. Alpha I is also greater than equal to 0, right? Because both sides, because this has to be greater than equal to 0. This is with constraint. So then that basically means these two things, the one of them has to be 0, right? One of them has to be 0. Now we know from our argument in before, there are only a few points is going to be satisfied yi times this guy equal to 1, which is the boundary. Most of points, they are actually bigger than this is majority point, not on boundary. So majority points, for majority point, this term actually does not equal to 0. Right? So if they are not equal to 0, which means alpha I has to be equal to 0. Okay. So from here, basically what you can see is most alpha i's is going to be equal to 0. Okay. So because majority of them, they are not going to be on the boundary, so therefore they are corresponding alpha I, the Lagrange multiplier has to be equal to 0. Okay. So that's this is a now if majority of most of alpha I equal to 0, okay. If you look at here, we come back to the equation 1. That means only a few, because if alpha I equal to 0 is not going to contribute into the beta. Right? So the only thing define the beta are those points with alpha I not equal to 0. All right. So this is where the supporting vectors come into play. Those ones with alpha I is bigger than 0 Okay, these are called support vectors. Because only those points with R5 bigger than 0, they're gonna contributing to the beta, which define the separator, linear separator, right? So therefore, this is then now this the everything kind of connects, right? The intuition, we can see the separator is only defined by a few points on boundary. Now mathematically, you can see this is also true from the derivation, right? Majority of them, there are Ri is equal to 0. You don't contribute to the beta, which is defined on separator. Only a few points which are sitting on the boundary with Ri bigger than 0, you're going to contribute to beta. Okay. On this beta, you can see beta is just a linear combination of this x's. Okay, it's only the linear combination of this x's. Okay, so essentially, this is what we this is what I wrote on the whiteboard. Essentially, explain this slides. So we want to find beta minima for this guy, right? We need to optimize the quadratic function, subject to linear constraint. The quadratic optimum problem is a well-known mathematical program problem, and many algorithms can do it. Okay, so the solution involves constructing dual problem, where Lagrange multiple Rphi is associated with every constraint in the prime problem. So this is what we define here. So we need to have in this is the dual problem is what I wrote essentially what I wrote on the blackboard. So we need to maximize this is a Q alpha, which is in terms to the Lagrange multiplier. Subject to constraint is Rphi has to be bigger than 0. Oh, and another constraint is summation Rphi yi equal to 0. Okay, which is the second condition, right? This is what we derive here. So summation Rphi and yi has to equal to 0, subject to the one set of the inequality and the one set on the one inequality constraints. So this problem is not that hard to solve. Okay. Now beta, yeah. J. This is just when you do this two summation, these are two separate summation. So I and J just two dummy variable, which is indexing for one is for this summation and one is for the second summation. Okay. So when you try to do this, if you don't have J, okay, if you have the same index, so I from 1 to n, this is also I from 1 to n. Essentially, they become there's no cross term. They just become the square of these two terms, right? But we do here, this is because this is summation is I from 1 to n. This is summation J from 1 to n. That just indicating there are summations of two sets of summations, and you multiply them, right? This is just like you have x1 plus x2 plus xp times x1 plus x2 plus xp. When you try to write in this summation, you're gonna write a summation I from 1 to n of x I multiply summation j from 1 to n of xj. Then these two things can be written as summation I from 1 to n summation j from 1 to n of xi xj. Because then there's going to be a summation of the cross terms, right? So the I and the j, they are just dummy variables. They don't contain any meaning. This is the j is basically here. The first summation you can view the summation I from 1 to n. The second summation is summation j from 1 to n. Okay. This is summation because they only have one, right? This is just summation over all the points. Any other question on this? All right. Now the optimum point, like I said, so the beta once you solve this problem for alphas, right? For this alpha i's, then we can just plug it in. And we can get in all beta. Like I said, most of alphas they are just equal to 0, so they don't actually contribute to the calculation. Only a few of them with alpha bigger than 0, you're gonna contribute into the beta. So once you have alpha, the beta is defined. Once your beta been defined, okay, then we can just define B equal to yk minus beta transpose xi k for any k such as alpha k does not equal to 0. Because for any alpha k, if they are not equal to 0, that means xk is at the boundary, right? If xt at the equal to boundary, then we know yi, we know beta transpose xi plus b, this is going to be equal to 1, right? Well, equal to yi times this guy. If they are at the boundary, we know yi times this is beta transpose xi plus b will be equal to 1, right? Because this is a property boundary. Now, if this is equal to 1, remember what is yi? Yi is equal to 1 or negative 1. So therefore, yi square is equal to 1, right? Because it's equal to 1 or negative 1. So therefore, this is going to be equal to yi squared, okay? Now, then this essentially just basically beta transpose xi plus b. This is going to be equal to yi because you can cancel one of yi on both sides. So b, then the b is just equal to yi minus beta transpose xi. Okay. So once you're having this, I should use the k because the system is in the slide. So this k defined as the k defined. Okay, so for those on the Zoom, basically this is what I wrote here. Because yk is yk equal to 1 or negative 1, so this is a yk squared equal to 1. So you can have this is the same, the b essentially that's yk minus beta transpose sk, right? So that's we have here, we have the in there. So the whole thing is then the whole thing is we have original problem. We try to maximum margin, subtract to a constraint. We convert that problem to a Lagrangian dual problem, right? We maximize this LD, and this maximize LD. You can see which is transformed to the problem down below. This is a quadratic problem, which is not hard to solve. So we work on this is a problem. We can subject to constraint also and summation of alpha I y equal to 0, right? Because summation of alpha I y equal to 0, that's from the constraint from the second equation we derived. Now, once you solve this, we have alpha and beta I. So once you have alpha and beta I, you can plug in back to this beta formation. Then we can because once alpha I is known, yi(x) is known, and beta is known. Once you have beta is known, then you just find out one point. Okay, find out one point such as this alpha k is not equal to 0. For those alpha k is not equal to 0, you plug in this beta into this point. Then you can have in the b will be equal to beta k minus beta transpose xk. So therefore you have b as well. Now for every b, okay, you find any point, they'll give you the same b value. Okay, so it doesn't matter which support points support vector you're using. It's the same. Now, is this clear, or is there any question on this? SVM is actually a very, I would say, is a very elegant algorithm, because you start with some kind of intuition, right? You start with some intuition, which is just you have two perfect separate group. You want a maximum margin, and then you have an intuition to see what is the best line. You will be somewhere in the middle, right? Now you're formulating that intuition into a mathematical form, and then you work on this mathematical form, and then now you're basically having a algorithm to work on. To me, this is to having this process. I mean, the people who the first guy to derive this is definitely a genius, right? You can see the math and intuition, they sort of line up together. Okay, I think this is a great example to see how you is actually very inspiring. But this is not all. Okay, you're gonna see is actually there are more amazing property from SVM. But keep in mind, okay, what I'm trying to introduce here is not just SVM algorithm itself. This class is about the big data analysis, okay? So what we try to do, we are going to go at the end is how to apply SVM to the big data analysis, okay? So keep that in mind. Don't lose. But in order to do that, we have to understand the SVM first, the algorithm, like every single detail, that's like we did for the logistic regression. So, but don't lose focus. Just the SVM algorithm itself is elegant, but we're going to go. See, you also should keep in mind how we should go from this is a single algorithm to the big data, okay, to the how to handle big data. But let's look at the algorithm first. Now, there's a very interesting property is if you have a new data points xi, x come in, right? It's a new data points x come in. If you want to make a prediction for the xx. So what's the prediction does it look like? The prediction basically is going to be summation of alpha yi xi transpose, because this is your beta, right? This is beta. So this is the first term is just beta transpose x plus b. So if you have a new data point, if I have a task point x comes in, and then when you try to make the prediction on the new point xi, so you only, okay, you can see the prediction only rely on the inner product between this new test point and your existing point, okay? So this is it only relies on the inner product between the test point x and the supporting point xi. And we will return to this later, okay? This is a very interesting point to that. We can make a good use of it. Now, also keep in mind, solve the optimization problem. It's just involving computing inner product xi transpose xj between all the training data points. You can look at here. When you try to solve this problem, all you need to do is just basically you just need a xi transpose xj in your computing here. That's all the points you do here. What does this mean? This just means if I can define, okay? If I can define a function, say if we can just define a function, this is to be say instead of xi transpose xj, if I can define some transformation of xi, okay, if I can make another vector of xi, so then xj, then this form here, essentially this is a solution is gonna be h of xi transpose h of xj. It's still gonna be just like if you transform your xi, okay, xi is a vector, right? If you transform your xi to a different vector, okay, to a different vector, and then this can also be defined on that vector as well. This inner product. So therefore, your solution, okay, then your solution, which is when you do the prediction, then the solution is going to be summation alpha I yi of this x h of xi transpose I from 1 to n times h of x. This will be your new. This will be your new the prediction the so like the new predicting function. Okay, so what it does this thing basically is the optimization problem itself and the solution itself only depending on the inner product between the supporting vectors, inner product of the feature or the feature vectors x's. So therefore, if I can make a change of this xi, okay, if I make change of this xi, then make it into say, well, I can. This will be later on. We're going to talk about to augment your vector space, okay, to be like making to be like a higher dimension. Then all the solution and all the properties still stay the same. Okay, it doesn't really change anything. Say if you're making your x, for example, your x is x1, x2, right? This is your original vector. Okay, yeah, two-dimensional. Now, if you're making your hx, okay, you're making another one. Say making this to be x1 square, x2 square, x1 times x2 or x1 square x2. You can say you can like augment it. Okay, you can try to do the augmentation to making this to be into like a higher dimension. This has become a 4-dimensional vector, right? This vector is still your feature vector because this is just like a 2-dimension, not become 4-dimension. Then you can essentially plug in this into the solution right here. Okay, into here. It doesn't really change any for algorithm-wise, doesn't change the complexity of the algorithm. But now you can basically the solution or everything is just still can push it through, right? It can push it through. Okay. So this is what I'm saying. I'll come back later because for the nonlinear SVM, okay, we rely on this property. Okay, just keep this in mind. We just in the next class we're gonna talk about it. Now, let's before we go there, let's talk another topic. Is called the soft margin classification. Now, what if the training data is not linearly separable? Because now we're working, we did like in an ideal, the scenario where they have two groups, which is the two groups can be perfectly separable, right? Well, but in reality, this you have two group points. Typically they can mingle together, right? There's some the blue dots is going to be in the red group, some red dots is going to be in the blue group, and you will not be able to perfectly separate them. Okay, so then if SVM can only handle perfect separable group, then this is not practical. So therefore, we have to solve this problem first. This, if you having this is a training set which are not perfectly linear separable, then we introduce a concept called a slack variable. This is psi I. Okay, so slack variable psi I can be added to allow misclassification of difficulty or noise samples. So psi I essentially is a distance of your points to the is basically you're adding another variable psi I, which is can allow the points can go to the other side. Okay, to the other side. In the let me see if I think I might have so mathematically, okay, let's look at math first, and then I'll come back to the slides for a little bit more illustration. So the original formulation is like this. We have to say the phi, we want to minimize, this is the beta transpose beta subject to all data points is on the right side, right? The minimal distance for the sign distance is at least 1 from each side. Now, the new formulation to including to say I'm still going to minimize this is a beta transpose beta, okay? But now I'm including another variable psi I to each point, such that each point yi times beta transpose xi plus b has to be bigger than or equal to 1 minus psi I, and the psi I has to be equal to, has to be bigger than or equal to 0 for all I. So if psi I equal to 0, okay, if psi I equal to 0 or equal to 0, that basically means every point is gonna, so psi I has another name is called slack, is a slack variable, right? So if the psi I equal to 0, okay, if all the psi I equal to 0, that basically means every point is gonna be the distance at least 1, right? At least 1. Now, if a psi I is equal to 2, for example, like psi equal to 2, that means this is going to be bigger than or equal to -1. Bigger than or equal to -1, that means for that group, I can cross the boundary to the other side, right? Or equal to 2.5, I can even move away from that boundary. Because remember, the boundary in the down below here, this is -1, this is 1, right? So if for the red points, if we want to cross the boundary to here, that means the distance to the boundary is going to be negative value, okay, negative value. So therefore, by introducing this psi I into there, is basically I'm saying I'm allowing my points can go to other side of the boundary. Okay, this is what it means. Now, of course, this psi I cannot be like a very large because if the size is too large, then I basically has no no control for the points, right? So therefore, the psi has, first of all, is psi had to be bigger than or equal to 0. Second term will be I want to minimize, okay, summation of psi. I want to give in some slack list to some points if it's hard to classify. But for most points, it should be on the right side. Okay, most points actually, so therefore their psi should be 0. Only allow a few points can be going to the other side. Therefore, I'm trying to minimize this side, gonna make that control. Because if you don't really control it, then your line, you basically can draw any line. Then it doesn't really matter, right? So therefore, the minimize the summation of psi, that's just basically saying I want to make most of my points on the right side. So therefore, their psi equal to 0. But then there are some of them can be go to other side. If I really cannot separate them, I'm saying I'm allowing them to go to the other side, to the boundary. But I want to minimize this, make this value as small as possible. Okay, as small as possible. The parameter C here is just you can view it as a way to control the overfitting. The C sometimes is also called a budget. Okay, it's called a budget. That means how much budget you can give into each point. So now look at this. So the psi essentially is the distance for the points. If for the blue points, okay, if you see the blue points, if it's on the right side, okay, if on the correct side, like for those ones below this is a separator, their psi basically has to be equal to 0. Okay, if it's on the other side, so therefore this value is wrong because the psi should be the points, or psi should be the value of this blue point to its boundary. Okay, and if it's to the separator, this is 1 minus psi. So there's a typo here. I should make a correction in the next time. So this should be 1 minus psi because this is a psi itself. This point to the boundary, to this boundary this is psi. And if it's points to the separator, it should be 1 minus psi. Okay, so that's okay. So that's hopefully this is now it makes sense to you. By introducing this psi to the in there, we basically allow them to be able to go to the cross the boundary. Okay, that's leaving this is a handle. This is a so like if they cannot be perfect separable, then using this soft margin, they can handle that. So this is a problem called soft margin classification. Okay, so if you writing out so the problem here is the same. The only thing we have in here, we have in the actual term psi in the objective function, want to summation of psi, want to minimize it, and we also have another. This is inequality constraint psi is bigger than or equal to 0. So therefore, all the things are the same. You can write out the Lagrangian function for this problem as well. Okay, for this problem as well. By using the same argument, okay, by using the same argument for the old problem, you can write out this Lagrangian function, and you can try and find out it's a dual problem. Okay, you write out LD in there, and you take a derivative with respect to beta, b, and the psi I. Okay, and you go through that. I'm not going to go through it, okay, because it's going to take in too much time. So you guys, when you go back, you guys do it by yourself, okay? Then the dual problem of the soft margin classification, which is a problem right here. The dual problem, okay? The dual problem. If you look at the formula, the Q alpha, this is your dual function, is equal to summation alpha I minus half of summation alpha I beta alpha j yi yj x transpose I x j. You want to maximize this, subject to summation alpha I yi equal to 0, and alpha I is bigger than or equal to 0, less than or equal to c. Okay. If you look at this formulation, if you compare with this formulation, okay, you can see they are almost the same. The only difference is in here, I'm having alpha is bigger than or equal to 0. With here in the soft margin classification, I have alpha bigger than or equal to 0. I have upper bound now, less than or equal to C. That's only difference. The select variable psi I and its the Lagrange function, neither select variable or their Lagrange function, it appear in the dual problem. Okay, so by working on this by introducing the select variable into there, algorithm wise, it's almost the same. The only thing is adding up bound to for your Lagrange multiplier of I. Okay, other things the same. Now, from this problem to this dual problem, there's a middle part. Okay, that derivation I'll leave as like take home the homework. Okay, this is for assignment for you to work on it. Okay, so you guys need to figure out. This should be very simple. Okay, I already just follow what I did on the whiteboard. You should be able to figure this out. Once you have this, then basically you solve the Fi. Okay, all other arguments are still valid. Okay, all other is still valid because then your beta is still equal to summation of I y xi, depending on those support vectors. And the B, you can just say now instead of you can just pick like one supporting vectors. This supporting vector could be the one on the boundary, or could be the one within the on the right on the wrong side. When you are on the wrong side, you're gonna have a psi k, right, for the select. But either one, if you pick one of them, okay. In here, I'm just trying to say using the maximize alpha k, but is essentially just saying anyone within the, because if you take the max alpha k is guaranteed it's not 0, right? Because it's guaranteed not 0. So we can solve in the beta and the B for the soft margin as well. Now, again, neither beta or B are needed explicit for the classification. When you're having a new X comes in, this will be your classification function, fx, right? You don't actually need explicit about beta or need about B, okay? Because what it need is inner product between xi and xj, right? Because look at this problem and this problem right here. Only what you only need is the inner product by x-axis here. So therefore, if this is the case, okay, we can actually transform. This is what we're gonna do in the next class. We're gonna generalize from the linear SVM to nonlinear SVM by introduce the concept kernel, okay, into there, where you can really making this as a SVM to be more powerful and is like more applicable in the real world. So the classification right now is still separating hyperplane. And the most important, so-called most important treating points, okay, are support vectors. They define the hyperplane. Now, does it mean those points that does not define the beta, they are not important? Do you think since our classification only rely on the points which are support vectors, doesn't mean all the rest points, like the points away from the boundary, are not important at all? What do we even use them? Do we even use those points away from the boundary? Well, we actually use them. Okay, we just use them. So like in this maximization problem right here, when we try to solve this problem, we actually have to define like all the points, the inner product between all the points. Okay, so you can think about it this way: those points are further away. Those points are further away define the boundary. Okay, even without the points further away, you don't know where the boundary is. Okay, so therefore, although those points did not appear in the solution in the function, but they are still used. Okay, in the part of the problem, they are part of the problem defined this point. Okay. Okay, all right. That's all for today. In next class, we're gonna talk more about the SVM. I'll see you guys on Wednesday.